So meanwhile, you guys can introduce yourself, like your name and from which branch you are or what you're pursuing, if, and then or any other details that you'd like to share and why you specifically took this course of mechanical operations. If you're comfortable, then you can speak up or you can also let me know in the chat box.
Sir, I am Vigneshwaran from MGR University. It's in Coimbatore. I'm a mechanical engineer, second year, later student. Actually, I like to understand the operations. That's really easy to making some products or how it's work. I really like to. I really like the operations. That's why I picked this. Sir. Thank you.
Okay, that's nice. So anyone else? So I think we can start our session for today. So let me just share my screen. So good evening everyone. Welcome to the week 1 live interaction session for this course Mechanical Operations. This course is offered by Professor Shabina Khanam from the Department of Chemical Engineering IIT Roorkee under the NPTEL SWAYAM program. Myself Pratyumnan, a PhD scholar from Department of Chemical Engineering IIT Guwahati. I am a course team member who will be conducting the live interaction session for this course for this particular semester, July November 2026. So, since this is our very first live interaction session, so we will discuss more on the fundamentals of mechanical operations. So, as you have when I hope most of you would have went through the course. So if you see, this is a 4-week course, so which will pass by very quickly. So it's just a matter of 11 lectures if I am not wrong. So let's try to make use of the time that we are here in this live interaction session. So since today is our very first live interaction session, so we would first like to discuss on mechanical operations, learn a little bit or have a brief overview on what is mechanical operations before we actually progress towards this characterization of single as well as collection of particles. So as such, when I talk about mechanical operations, what do you people think about or what comes to your mind when I say the word mechanical operations?
Sir, it's the process of making the material or how they handling the material or how we designing the material, something like that, sir.
So basically, we like to see how do we operate on the materials. So basically, mechanical operation as such, if you see, is a subject of study. which particularly deals with particulate matters, basically speaking with particles. So here in mechanical operations course we would particularly be interested to learn about the processing, handling, characterization and conversion of the particulate matters. Basically speaking, we will be more interested towards understanding the particles as well as the powder. So both particle technology and powder technology is something that we will be focusing on. These both will be of our primary interest in the course mechanical operations. So the major reason why this particular um, branch of study came out to be as a topic of interest is primarily because these operations or the mechanical operations are being used in different fields. Like almost every field deals with materials, so they need to process them, they need to handle these materials, and they need to know the ways to handle these material and characterize this material. So it becomes more of a industrial significance when we deal with this course on mechanical operations, and that is primarily the reason why mechanical operations is very important to study, because we need to know how to handle the particles. Because as if you would have went through the course, you would also be able to understand that with particles shape and size, their properties actually varies. So the way the particles pack, the way the particles shape and sizes are, influences the properties of the particle, which directly influences the way these particles are processed, which influences the final application uh, of the particles and the powder material that we are handling. So basically this mechanical operations is something that we are dealing with for a very long time. So if you would have went through the very first um, lecture of our course mechanical operations, you would have seen professor discussing much on the history of the mechanical operation. So how these mechanical operation techniques have been evolved and how they have been previously used in the everyday life. Like for example, techniques like winnowing, threshing, and then the equipments like mortar and pestle, and then the Indian grinding stone. So all these are something which are conventionally used in our home, but they all deal with some sort of particles. So they all come under the group of mechanical operations. So that is why it becomes an important to study. The reason is we need to know how to handle the material. So if we do not know how to handle this material, then probably using them for particular application becomes a very difficult task. So that is one of the reasons why mechanical operations is a topic of interest. And to say how the particle shape or size affects the properties of the material or the final application, the best example that was given was, it's about the um, how this particle size influences your chocolate taste. So the mouth feel concept. So if you see that particular table in the course content, you would have seen that for the chocolates a particular particle size is required. The major reason why that kind of a optimum particle size is required is basically because this um, only then we will be able to get a good viscosity, and that's when you will have a proper mouth feel, or you can actually enjoy the taste of the chocolate. So suppose if the particle size is not to the optimum level, then probably the viscosity will not be fine, will not be optimum. So as the viscosity is not optimum, it will be, you won't be able to get the same taste as that of the other chocolates that are available. So suppose if brand A has a particle size, or brand A chocolate has a particle size of certain of a optimum range, whereas a brand B does not have that optimum range, it is kind of like very different, then you will not like brand B chocolate because that does not taste properly, whereas you will be more attracted to branding. So here if you see, based on this particle size, it affects the production quality of the particles. That is the reason, as we keep going towards finer and finer and finer particles, and then as we keep refining our process to get the optimum particle size, the um, cost that is involved in the production also increases, and that is typically the reason which gets reflected on the consumer end as well. So cheaper chocolates will not basically have that level of mouthfeel or the particle size optimization compared to the chocolates that are expensive. So expensive chocolates predominantly focus on this particular properties of particle size, so that they can optimize the viscosity, so that it can directly influence your mouthfeel or the taste that you see. Similar to the chocolate, what do you say? Uh, Similar to this chocolate example, another example is the medicine. So depending upon the size of the particles that you use, the amount of surface area that is exposed to the target organ varies. As that varies, so if you have, so based on the size of the medicine that you take, the exposed surface area of the medicine varies, and based on that their dissolution rate varies. So if you do not take, or if the medicine is not of an optimal size, what problem happens is that the exposed surface area will not be enhanced or will not be optimum. That will affect the dissolution rate, and this typically depends on the delayed action of the medicine on that particular target. So these are the two examples on how important, or specifically in the field of medicine, you can see how important it is that the particle size influences your material or the final product that you're intending to do. So this is typically the reason why people are interested to understand about particle technology and the particle size analysis, and would like to understand deeper on how varying the shape and size of the particle influences the final application of the material. It's not just about the final application. Even this particle size typically influences your properties of the material. So if some of you would have taken this course on nanotechnology, have anyone of you have ever taken a course on nanotechnology by any chance?
No, sir.
Okay, so in the field of nanotechnology, if you see, as the size of the particle goes from a macroscopic scale to a nanoscopic level, that is in the order of 10 power minus 9 meters, you can see that the properties varies in a very drastic manner. What properties that you observe for the macroscopic material may not be the same, or you may get a completely different property when you break down the material to nanoscopic level. So that property differences happen with the particle shape, and when you move from macroscopic to nano or microscopic level to nanometer level, that property change becomes more pronounced. And when I say property change, it's not just about one or two properties. I mean, it typically influences your optical property, electrical property, magnetic properties, mechanical properties of the system. So that's how the particle size influences your properties of the material. So gold, as such, when it remains in a microscopic level or in a macro scale level, it behaves differently, and when it actually goes to a nanoscopic level, it operates or it exhibits properties that are totally different from what you can observe in the microscopic level. So if you are typically interested, you can actually go and look in the internet on this, about how the property changes when you go from macro scale materials to nanomaterials. So this is about, so basically what we wanted to emphasize is why mechanical operations is an important field of aspect, because of the particle size and the shape. Since we are dealing with particles and particles comes in various forms, various size and shapes, we need to characterize them, understand them, so that we can use them for intended application. Each and every application or each and every target application that we have in mind will basically require the particles which are different in shape and size. So we need to be aware of that as engineers, or as a particular as engineers who are working in this field. We need to know what kind of particles or what kind of particle size and shapes are required, so that we can handle them better, and we can do the process more efficiently, in such a way that the application what we are finally targeting operates more effectively. So that is the place where we are now going to shift our focus, which is nothing but is the characterization of the particles. So here in the characterization of the particles, we would primarily be more interested towards discussing on the size and the shape of the material. So there are only three things that we will be interested. So let me just uh, so in case of single particle characterization, the first one is, so so the descriptors that you can say, or what we would like to characterize this single particles is is it in terms of its size, second one is shape, and third one is its density. Because these solids needs to be processed and they come in varieties of shape, so for their processing we need to be aware of the shape, their nature and their behavior. So typically speaking, we need to be aware of their size, shape and density of the particles. So first let us talk about the size of the particle. So as such, if you see, when we think about the size of the particles, so for regular particles like any kind of polygon, like triangle, square, or in case of three-dimensional, you can say pyramid, um, cuboid, these are regular particles. So they have fixed dimensions, basically speaking. That is the reason, because each and every the dimensions of their particles can be easily specified. However, majority of the solid particles that you're going to use in an industry, we go to a processing industry, then if you're going to basically deal with the particle over there, when you deal with particles, those particles are not going to be regular in its features. They are going to present a very irregular shape to you. So at that time, we need to understand how to process these particles. So if you're going to take a bulk of a material, let's say you take a big chunk, in that particular chunk, it can be possible that each and every particle that you see maybe of a different shape, different size. In fact, it can even, in fact, in majority of the cases, it can be even, but it can be even that it has its own shape and size. Like each one is totally different, totally irregular. You cannot even characterize that particular shape. So in that case, that is the nature of the solid. But as such, when we see as engineers, it is very difficult for us to see how to use these particles, right? So we need to be, I mean, we are human beings, we have certain limitations. So in order to basically understand about these particles which are irregular in shape and size, we cannot go on looking at each and every particle and then start measuring them, or basically we cannot take every particle and then note down their dimensions, like unlike you do it in case of a cube or a cuboid, because if you have a homogeneous regular solid particles, they are going to have similar dimensions, length, breadth, and in case of sphere, you have only one particular, that is your sphere, sorry, that is your diameter. In case of cube, you have only one dimension, that is your edge length. In case of cuboid, it is two. And similarly, for regular polygons, it's very easy to specify their numbers, uh, uh, the, their numbers specifically, the length, breadth, and height. However, in case of irregular particles, we do not have that amount of we cannot easily characterize them, unlike how we do for regular systems. So that is typically the reason why we always characterize this irregular particles. We find the regular equivalent of them. So we try to find the equivalent regular shape for them, and then based on that we try to make, or we try to analyze these particles. Since sphere has only one dimension, that is nothing but it's your diameter, so we consider majority of the irregular particles, we find their spherical equivalent, and once we do find the spherical equivalent of these particles, we can easily characterize them. So the very first thing that we do is, when we get a irregular particles, we find their spherical equivalent. And what I mean by spherical equivalent is nothing but we equate the dimensions of the particle or to that of the sphere. And in order to do that, we basically have multiple different ways on how we define the particle size. So defining particle size. So in order to define these particle size, specifically the irregular particle size, there are two different types of definitions. One is the Martin's diameter and another one is Ferret's diameter. So anyone who knows the definition or what does this Martin's diameter and Ferret's diameter means?
Sorry, sir, no, sir.
Excuse me?
No, sir, no.
Oh, okay. Just a second. Okay. So Martin's diameter is nothing but, so for any irregular particles, I'll read it out. That would be better. Length of the line bisecting the maximum cross-sectional area of the particles. So, you take a irregular shape particle, you find the area. Now you need to find a line that actually bisects this cross-sectional area of the particle into two different halves. That length is called Martin's diameter. Then another one that you have is the ferret's diameter. Ferret's diameter is quite simple. Here what is the thing is, it is nothing but it is the distance between two extreme points on the particle surface. So when you take an irregular shaped particle, the two extreme points, so any two for any irregular shaped particles, if you measure the distance between, you take a irregular shaped particle, let me just draw one here, because it's quite easy to draw a irregular shaped particle. So this is a irregular shaped particle. So now here you take any point, and then from that point you keep marking to multiple points. So let's say for example, I start here, I mark one line here. Let me just change the color. So this is one line. Now I do the same thing for throughout the surface of the irregular particle. The distance between the two extreme points, or wherever the length between the 2 points is the maximum for this irregular shaped particle, that length is called as the ferret's diameter. Now in case of Martin's diameter, you get to know the cross sectional area of the particle, and once you know that cross sectional area of the particle, you find a line that splits this cross sectional area into two halves. So maybe like this. It can be, I mean, this is totally a rough one. It's just for understanding. So it's not up to any scale, but just to show what Martin diameter and what Ferret's diameter is of. So this is the Martin's and the Ferret's diameter. So basically these definitions came up so that we can start defining the particle size, so that the particle size analysis can be done more easily, or we basically have a factor or a particular quantity with which we can characterize the size or analyze the particle sizes. Next we come to circular equivalent diameter. So there are multiple different what do you say, diameters. So we need to look at each one of them. So basically the thing is, we try to find the spherical equivalent for an irregular shaped particle, and based on that we and when we do this, we define certain parameters. So I'll list down the parameters. If in Please let me know if you know any of them. So first one is ds. So all this wait, let me just write down the entire stuff. ds, dv, ds, da, dw, dmin, dmax, and dself. So all this SV, they are subscripts. So here I have written it this way. So how many of you know these diameters, the definition of these diameters? ds, dv, dvs, da.
So dv is dependent variable.
Okay.
Outcome of results being measured, right, sir?
Can you come again?
The outcome of different result. The outcome of result being measured.
Okay. Anyone else, or for any other this thing anyone knows? Okay. So I'll write for one or two. You can see. So this is there in the course. So if you haven't gone through the course, then I would request everyone to go through, because we discussed what was earlier discussed in the course. So this is just to recollect, because over the week people may forget. So that is the reason. So for example, dA is nothing but diameter, sorry, diameter of the sphere equivalent to the size of the minimum square aperture through which the particles can pass. Similarly, if you see for ds, diameter of the sphere equivalent to the surface area of the particle. Likewise, dbs is nothing but diameter of the sphere equivalent to the surface area to the volume ratio of the particle. dw is nothing but to the weight of the particle. So these are the sphere equivalent, what I was talking about here, the spherical equivalent. So in order to know the spherical equivalent, we basically keep a property, or we basically fix a property, and based on that property we define the spherical equivalent for the irregular particles, so that we can easily handle them. So basically we need to know which property we are going to target. Based on that target property, we find the equivalent of that, the spherical equivalent of the irregular particles, and then do the particle size analysis. So this is about the particle size. Now we have to go for the particle shape. So like how I said that each and every solid particles comes in different sizes, similarly they also happen to have different shapes. So particle shape. So in order to define about particle shape, there are totally three ways. So the first one is circularity, second one is convexity, third one is elongation. So these are called as the shape descriptors. So based on these three properties, or you can say the parameters, we define the shape of the particles, or we classify the particles. So circularity, convexity and elongation. Any guesses on what it can actually represent?
The circularity means the particles may be the circle shapes.
Okay. For
The
convexity and elongation?
the convex concave shapes. And I don't know about the elongation, sir.
Anyone else?
No, sir. I don't know.
Yes?
I don't know.
Oh, okay. So, so this is basically circularity, as in what we mean is we basically try to see how much circular the shape is. So, for example, in case of a circle, the circularity is going to be 1. And for all these parameters, I'll write it here. We define the values for each of them between 0 to 1. Their values vary between 0 to 1. In case of circularity, for circle, if you see, the value is going to be 1. Whereas if you see a needle, like the pin and needle, over there the circularity is going to be 0. For convexity, it is going to be based on surface roughness. That is how rough is the surface going to be. And for elongation, it is going to be based on the length to the width ratio. So length and width, that particular ratio. So the exact definition, I'll just write it now. So you can note it down if you want. And as I say repeatedly, all these definitions and the formulas are covered already in the course. I'm just repeating here for just to so that everyone can recollect. So circularity is nothing but it is the perimeter of a circle that has the same area as that of the particle divided by the actual perimeter of the particle. Okay, this is circularity. Then you come to convexity. Just a second. This is convexity is nothing but area of a circle with the same area as that of the particle divided by the total area. And elongation is nothing but it's basically to check how elongated the structure is. So in case of if I say elongation for a circle, let me just write the value or the expression 1 minus width by length. So if I ask a question for circle, what will be the elongation? Anyone? For circle, what will be the elongation? As per this expression, 1 minus width over length ratio.
Sir, are you asking about the level width and length, sir?
Yes, I am asking what will be the elongation, that value for a circle.
Mm, I don't know, sir.
Okay, anyone else?
Is 0?
0, yes, that's correct. Because in case of a circle, if you see, they the circle as such, if you see a width and the length, it's going to be the same, right? Because both the values are nothing but they are going to be the diameter of the circle. So it's going to be 1 minus width over length. That ratio is 1. 1 minus 1 is 0. So elongation
Okay, sir.
is going to be equal to 0 for a circle. For a needle,
That's one, sir.
1. Yes, because it does not have a width, so 1 minus 0 is going to be 0. So for a needle, it is going to be 1. Now, apart from that, we also have to understand about certain other characteristics, or you can say the parameters, such as specific surface area, then sphericity, and then volume shape factor. So these also have similar definitions as like how you, I mean, similar definition as in the sense they have some formulas. So we will be discussing this one by one. So let's start with sphericity. The name itself could suggest a few things. Sphericity. So which means something that is going to deal with the sphere. So definition of sphericity goes something like this. Just a second. So sphericity is nothing but it is defined as surface area of sphere having volume or having same volume as that of the particle that you are going to take under consideration, divided by the surface area of the particle. That is the original particle that you are taking, that irregular particle that you are going to take. This is how you define sphericity. So formula for sphericity is nothing but so it's going to be, I'm going to write this as it is written in the this thing. So this will take few seconds. Pi dv square divided by just a minute. SP. So SP is nothing but it is the surface area of the particle. dB is nothing but, sorry, it is the diameter of the sphere equivalent
Volume.
equivalent to the volume, is exactly to the volume of the particles. So basically how you will be calculating is you will know the volume of the particle, which I'm going to make it as Vp. This you will be equating it to pi dv square cube by 6. I hope you can everyone can understand why I wrote pi dv cube by 6. So volume of a sphere is 4 by 3 pi r cube. If you express radius in terms of diameter, then the formula becomes pi d cube by 6. So from here you will be able to calculate the value of, from the above expression you can calculate the value of dV. So once you know the value of dV, SP will be either given to you or you can calculate on your own. So once you know that, pi dV square by SP is going to be nothing but the sphericity of the particle. And one more thing, shape factor is nothing but 1 by sphericity. So remember this. Now, based on this, we will be solving a problem. So, kindly remember on the steps or how to calculate the sphericity for a particle. Next, we have the specific surface area. So, whenever you get the word specific, it typically means that it you will have a physical quantity which is going to be, or you can say, whenever you have the word specific in front of any parameter or any variable that you have, it typically just means that it's going to be a ratio of that particular parameter, the physical parameter, upon mass. So the word specific indirectly means that it's a quantity that is going to be having a mass factor. So similarly, specific surface area is nothing but it is something that is going, it's nothing but the surface area upon mass of the particles. Same thing goes with specific density, specific gravity, all those things. It typically means that it is just nothing but it's that particular parameter or the variable, the physical variable that you're talking about upon its mass. So kindly remember this. It will be useful when you um, see, I mean, throughout the uh, at many places wherever you had whenever you come with this engineering terms. So specific surface area is nothing but the specific surface area of the particle divided by specific surface area of the sphere with the same diameter. But so it is usually expressed as n equals to SP, that is specific surface area of the particle, divided by 6 by rho, sorry, this is the specific surface area, the equation. I'll just highlight them. After this, you have another thing called volume shape factor. And why the font size, which is nothing but it is based on the volume of the irregular particles. So it is usually represented as A times D where A is the volume shape factor. So this is the total concept on the characterization of single particles. So any doubts so far before we move towards the collection of particles? Anyone?
Sir, can you explain about again the surface
Huh?
surface formula? Can you explain it again, sir?
Which formula? This.
SSA, specific surface area.
Yeah. So specific surface area is nothing but the surface area of the particle, which is nothing but SP, divided by the surface area of the particle, the specific surface area of the particle with the same diameter. So here surface area of the particle is SP. This divided by for this one, what you have to do is you have to consider the density, because here we are talking about specific surface area, right? So as I said, it's a mass dependent parameter. So over there they have made the volume adjustment. So you have mass and you have volume, so they made it so mass by volume is density. So that is the reason you have the value rho, and the d average is nothing but is the uh, diameter of the sphere.
Okay, sir. Thank you.
So then shall we go to collection of particles?
Yeah, sir.
So here we typically deal with PSD analysis. Sorry. So PSD analysis is nothing but particle size distribution analysis. So when you are going to have, so previously what we discussed was for one particle. Again, you are in an industry, when you go and then you are going to work, you are not going to work with single particle, right? You are going to work with the multiple particles. So in that case, we need to talk about the characterization, but instead of talking about characterization of single particle, here we will be talking about the characterization of collection of particles. So as such, solids, when they come in different shape and size. So in order to uh, handle them, so basically for each and every particular application, we need a particular size of particles. So we need to separate them. So this separation we basically do according to the size of the particle, which will be suitable for the industrial operation. So for that, in order to basically separate these particles, we basically separate them based on this particle shape and size, as I said. So in order to separate the particles for a particular industrial application, we go for PSD analysis, that is particle size distribution analysis. And this is particularly essential for any kind of chemical processing that you take, or even in case of mechanical processing, when you go for manufacturing plants specifically, we have to do these kind of PSD analysis. So the best way, or the most simplest way for doing a PSD analysis is through sieve. I hope you would have seen a sieve at your home. So they typically use that to separate stones or other larger particles from fine powder flowers, if you remember, if you have ever happened to see that. So sieve is one of the most commonly used equipment at a home, and even in case of some of the industrial what do you say, so even in case of industry, where we use them to separate particles of different size. So you will have a series of filter, and then we will load the sample depending upon the size of openings that is
Size
present
of
in the sieve.
meters, sir. Yes, and the small size will be coming outside from it, sir.
Yeah, so the small size will first go to the bottom, then the size that is a bit which is greater than that small size will come to the second. So when you have a series of filter based on the openings of the seeds that you have, you can separate the particles into multiple different size fractions, and then you can connect each one of them, and then you can use it depending upon what kind of application you want, you can use them. So that particular opening, so that is where the things goes, that is where we become interested in the sieve opening size. So these sieve openings are called apertures, and their size is called, sorry, it's called aperture size. So this aperture size of the screen is usually defined by a parameter which is called as mesh number. Have any of you have heard about this concept of mesh number?
Yes, sir.
Yes. If you have heard, then you can let me know. You can let me know what do you know about mesh number.
The tiny opening or in layer inch areas like sleeve,
Yes,
filter.
yes, something like that. So the exact definition is number of apertures, or to say it in a very or to say it in a easier way, number of openings per unit length, per unit of linear length. So in case in a particular linear in a linear scale, if you are going to have 20 openings, so the mesh number is going to be 1 by 20. Yeah, in a 1 centimeter of linear length, if you are going to have 20 openings, 1 by 20 is going to be the mesh number. So higher the mesh number, it means smaller the aperture size, right? It makes sense, because you are going to have more number of openings in a particular length, or of a particular length, in a particular length you are going to have more openings. So each openings will be going to be of a shorter, each openings is going to become small. So that's what, higher the mesh number, smaller the aperture size. And in order to for the scene analysis, multiple different countries have come up with their own standards. So we have American standards, we have German standards. Likewise, we also have Indian standards, Indian standard screen. Indian standard screen. So usually in all the other standards, we basically represent the mesh number as number of aperture per unit linear length. However, in case of Indian standards, it's expressed, this mesh number is expressed quite differently. So what they do is, or what they express it as, aperture size is expressed to the nearest decamicron. That's how the ISS standards define. In the Indian standard for screens, define mesh number, and this particular definition is going to be quite different from the American standards that are being used. So, so here our major focus is on doing PSG analysis, finding out the sample, doing the PSG analysis, and then trying to understand how to do this. So we have to do PSD analysis. Once we know the PSD analysis in a particular solid, we can say that these are the range of particle sizes that are available. So as engineers, we need to know how to do PSD or particle size distribution. For that, we basically use an equipment that is called sieve analysis. Again, based on different particle size, you typically go for different kind of techniques. Sieve analysis is the most simplest one. Again, there are limitations to this sieve analysis. You cannot analyze samples that have sizes lower than a particular range. So if you want to see that graph, it's here. So you see, in case, so this is the PSG method. Each, so in order for that particle size distribution, in order to do that, we have to basically use different kind of techniques, because all the techniques are not suitable for particles of all the sizes. So for example, if you see sieve analysis you can only do when you have a particle size above 40 micrometers. Whereas if you see gravity sedimentation, that is settling of the solid particle only by using gravity, in those cases the particle size range needs to be between 1 to 100 micrometers. If you see for centrifugal sedimentation, that is you use centrifugal force and then you cause the particles to settle down at the bottom. In that case, you have a particular size range. Like that, for each and every kind of techniques, you have certain size range. Sieve analysis is the one which is used for analyzing bigger particle sizes. Suppose if you are going to go down to particle size that are in the order of microns or even less than a microns in the nanoscale range, then you go for more sophisticated techniques like ultra microscopy, electron microscopy, X-ray scattering, light scattering, and so on. So depending upon the particle size range that you have, you basically choose the technique so that you can do the separation and their classification. So our discussion kind of ends here. Next, we will actually move towards problem. So that is the basic, what do you say, the aim of this session. This concept recollection is just to make sure that you do not forget anything, or it's just to recollect and revise what was taught in the course. So what we can do is, so I'll keep this slide on. If you have any doubts, you're welcome to let me know. Apart from that, let's take a 5-minute break. So we will start solving question 1 to, starting from question 1 and 2 after 5 minutes. So in case if you want to take a break, because it's a 2-hour session, so what I observed was in the previous session, continuously taking for 2 hours is of not much help to many. So that is the reason this 5 minutes break in between. So if you want, you can, what do you say? You can take the break time, or otherwise you can solve the questions and then have the answers ready, so that once we resume back, you can just let me know the answers, because these are not except for question 2, you don't need to solve for 1 and 3, so it should not take much time, I believe. I think 5 minutes is a fair enough time. So let us come back at 8:19. Sorry, 6:19.
Okay, sir.
So shall we resume?
Yeah, sir. Ready, sir.
Okay. I think it's shared only. Okay. My presentation is visible, right?
Yeah, sir. It's visible.
Okay. So let me just. So what's the answer for the first question? Which of the following is not a regular shape of the particles?
The needle.
So that's a simple question. So the answer is needle, because as such when I say regular shape of the particles, what the question means is it is a polygon. So the question is asking which of the following is not a polygon. So cube is a polygon, is a regular polygon. Octahedral is a regular polygon. Sphere, spherical is again a regular polygon. So needle is the one that does not have any kind of a regular shape. It's a irregular shaped particle. So question 1, answer is D, needle. What about question 2? The sphericity of a cylindrical particle which has a height that is equal to 3 times its diameter.
It's 0.78.
0.78. Okay. How did you do this problem? Can you just explain in?
1 minute.
Yes.
Sir, can I solve it?
Yeah, I mean, okay, yeah, you can solve it, but I mean, are you going to? Okay,
I'm
go ahead.
presenting, sir.
Hmm.
1 minute. 1 minute.
Okay.
Sir, my screen is on audible, sir.
Huh?
My screen is sharing, sir.
Okay, okay. I am just see. No, I cannot see. Wait, okay. Let me stop presenting and then let's see. I cannot see your screen.
1 minute. Now, sir?
Hmm. Yeah, wait. I can see only black.
Yeah, yeah, sir. And now you can see?
Yeah, yeah.
Uh, Sir, they give a height for 3, sir.
Hmm.
3, formula, necessity is formula is equal to
Okay.
surface area, sphere, same volume, sir. Actual surface area particles. Okay. Uh, so the height was 3D,
Hmm.
3 diameter. First, we are going to take a volume of cylinder.
Hmm.
Formula is pi r square h.
Hmm.
We have a h is equal to 6, sir. So pi r square 6, sir. So it becomes into 6 pi
Okay.
r square r cube. Sorry.
Okay.
Now we're going to calculate the surface of the cylinder. It's
Hmm.
U I T is equal to 2 pi r h plus 2 pi r square, sir.
Okay.
So we have a height is equal to 6. So 2 pi r 6 plus 2 pi r square. We put in the bracket. 2 6 are 12, sir. So 5 by r
No,
square.
H is 3R, no. Sorry,
It's
H
not,
is
sir.
6R,
Actually,
right?
1 minute. We did our last, sir, step 1 formula, sir, volume of the cylinder. I converted it into 6, sir. Then we put it into h is equal to 6r. So now 6r is equal to 12. 2 6 are
Oh, okay,
12, sir.
okay.
12, 12 by r square. Now 2 by r square.
Okay.
So total 14 by r square.
This
And
is
now
the
we
surface
are,
area of the particle. That is the denominator,
yeah.
14 pi
Yes,
r
yeah.
square.
The
Okay.
surface of the cylinder. Now particles. Yes.
Ah.
Uh, now into volume of the cylinders. Surface of the equivalent pair from 4 by 3 r pi r cube is equal to 6 pi r cube, sir. So now here is r is 18 by 4 1 by 3 uh, divided into 1.651
Which one is capital R and which one is small r here?
This one is capital, sir.
Okay, where the small r and
This one
the
is small.
okay.
Small r is 1.651.
6.1.
6.1 to r.
Ah, small r or capital R?
Small, sir.
No, but how
Small.
right left side also? I mean left side then it should be capital R, right?
Okay, this one is the from you. You seen the capital, yes, sir. This one is capital, sir. I put it into bracket 18 by 44 whole square 1 by 3.
1 by 3.
No,
Pi on each
1 by
side will
3.
get cancelled.
Uh,
Then R, then again one more R should be there, no small r on the right hand side.
it will get properly, sir. But this. This one is 2.
18,
4,
6
4 by
times
3.
3 is
Yeah.
18. 18 by
Yes,
4 is
sir.
fine. Whole power 1 by
Yes,
3 is
sir.
fine. Pi will get cancelled. Right?
Pi means,
RHS,
sorry, I can't get it, sir.
the pi, the 22 by 7, 6 pi, that pi.
Yes, sir.
That will get cancelled on both the left hand side and right hand side.
4 by 3 into 5 r by 3 is. I did the one math that it get it correctly, but I did this. Sorry.
No, this is fine. 18 by 4, 1 by 3 is fine. You need to
Yeah.
multiply that with small r. Capital R is equal to 18 by 4 whole power 1 by 3 times small r.
Oh. Yeah, sir. Yes. All right.
Then you will get capital R as 1.6512 times small r.
Yes, sir.
Then proceed.
Then we get by
Now
surface
surface
of the
area of.
sphere, sir. Surface of the sphere, sir. 4 pi r square. Now we need to 4 pi by 1.651 square r square, sir.
Okay.
It gives 10.9 pi by r square.
Okay.
Yeah, now we need to specificity, sir. Needs to equal to pi. Last is 10.9 pi r square divided by first one we did, sir. This one
14
formula.
14 pi r square.
14 pi r square. pi r square.
So pi r square get
Uh,
cancelled.
pi r square answer. Potential. Now we get it into 0 point something.
0.778, but yeah, that is fine. 0.78. So yeah, that's excellent.
778.
So,
Yeah.
thanks Vigneshwaran for solving. I think probably I have been conducting this live interaction session for the last, if I'm not wrong, since Jan 2024, and I have never had anyone coming up and solving on the live session. So yeah, thanks for that. So
Okay, sir.
the answer is 0.78.
Yes, sir. Thank you, sir.
Yeah, thank you so much
Thank you.
and good work. So,
Thank
any
you.
doubts with respect to this solving of this sphericity?
No, sir.
Okay.
Actually, the third question is I'm confusing about this, sir.
Okay,
Actually,
let's
most
come to that. Now, since we know the sphericity, calculate the shape factor as well.
sir, you didn't present the screen, sir.
Sorry, sorry.
So,
Sorry,
okay,
sorry,
sir.
sorry. Thanks for letting me know. Yeah, it's now visible. So 0.78 is the answer, and if you have others, if you have any doubts, please let me know. We can solve it once again. Apart from that, apart from calculation of sphericity, how do you calculate shape factor? I gave the formula for shape factor actually in the while going for the, I mean, while discussing the concepts.
Sir, I think the answer was none of these.
No, no, no. No, I'm not talking about question 3. I'm talking about question 2. Calculate the shape factor, that shape factor, the value. I still didn't go to question 3. Shape factor is nothing but it is 1 by sphericity. So that is 1 by 0.78. You can calculate that value. So any doubts related to question 2, others, how to calculate sphericity, I will be posting the answers. Not I will not be solving it here, but but then this presentation will be available to you. So at that time you will get the solution for this question as well. But again, if you have any doubts, you are welcome to let me know. We can solve that problem before we progress towards the other ones. Because you may expect these kind of questions in your assignment as well as in your final exam if you plan to take for this course. Okay, then let's progress towards question 3. Question 3 is the common factor in Martin and ferret's diameter is A. Length of the line bisecting the maximum cross-sectional area. B. Distance between the two extreme points on a particle surface. C. The projected cross-section area of the particle. And D is none of these. Somebody told, I think the answer was D, none of these. Anyone else? Just a second. Okay. Give more. Oh, I think there was a network issue. So,
Okay, sir. No problem.
yeah. So, yeah. So, question 3 is the common factor in Martin and ferret's diameter is. So, please be careful with the word common factor. So, it's not like they are asking you the definition of Martin or ferret's diameter. They are asking you what is the common aspect that is there in both of them.
Okay, sir.
So, what will be the answer? Anyone? Answer for question 3. So let's look at the figure. Let's look at this figure. Oh. Now, what do you think would be the commonality between this Martin diameter and the ferrous diameter? Look at this figure. This one. You see a irregular shaped particle, and then you see that one is the Martin's and another one is the ferrous diameter. Martin is basically nothing but the length of the line that is bisecting the maximum cross sectional area of the particle. Ferret is nothing but it's basically the distance between the two extreme points on the irregular particle surface. Now, what is going to be common in both? Again, think from the one clue is we are talking about particles here. Think from the perspective of dimensions between what I told and what I draw. So I said particles, but here I drew a what do you say? What do you say? A plane figure, a figure on the plane. So think from that dimension aspect, then you'll be able to get to the answer.
Sir, can you show the question?
Oh, hmm. Oh, sorry. Hmm. Question 3.
Sir, I think the project cross-section area of the particles.
So option C is the projected cross-section area of the particle is the common factor. So see particles as it they have three dimensionals, right? Three dimension particles they are. But then when we discuss about the concept of Martin and ferrets, if you see I have drawn a figure on the plane. So it is the projected cross-section area. So both these diameters are typically defined for the projected cross-sectional area of the particle, not for the particle itself. So they take the projection of that particle, and with that projection they define the Martin and the ferrets diameter. So the particle is irregular. That is the reason if you see the projection is like this. In case if you take the sphere, the projection is going to be a circle. If you take a cube, the projection is going to be a square. For a cuboid, it is going to be a rectangle. So in this case, the answer is projected cross-section area of the sphere. That is the common factor behind in the Martin and the ferrets diameter. Because if you see, option A is Martin's diameter and option B is ferrets diameter, right? So that is the typical definition. There is nothing that is going to be common in them in both of these. So this is about question 3. Any doubts related to this?
No, sir, you already explained, sir.
No? So anyone else? Any doubts?
No, sir.
Okay. Let's go to
Sir,
question.
sir,
Yeah.
can you zoom out this sheet? You
Okay.
can take the notes for the
Okay. Okay. Hmm.
first 1 to 3 questions.
Oh. Hmm. This presentation will be uploaded, so you can
Okay,
access
sir.
it there as well.
Okay. Thank you, sir.
Let's go to. Okay, let's see how fast we finish question 4, 5, 6. Specific surface ratio is defined as specific surface per unit area, sorry, surface area per unit mass, surface area per unit volume, surface area per
Sir,
unit length.
option
Option
A.
A. So as I said, whenever you have anything that is preceded with the term specific, it typically means that it is that particular quantity upon mass. So specific surface ratio is nothing but it is surface area per unit mass. Then fifth question. Water mills are used for dry grinding, size reduction, increasing particle size, or wet grinding.
Wet grinding, sir.
Wet
Wet
grinding.
grind.
Because watermills typically use water, and then there is that vertical shaft which helps in basically mixing, and that is called as wet grinding. Question 6. Success and
Size of the particle, sir.
Size of particle.
depends on the
Size of particle.
size of the particles. Yes. Because as we discussed in that example, right, that chocolate,
Yes,
their
sir.
viscosity depends on the size. So a success or a failure of a chocolate depends upon the size of the particle. If you have an optimum size, the mouth feel will be good, so you will find it more tasty. Whereas in case if the particle size is not going to be in the optimum, then you will not feel that level of taste that you will experience with the other one. So I hope there are no doubts with question 4, 5, and 6. If not, we can proceed.
No doubts.
Now, okay. So question 7. A rectangular particle is having you 6 times 1 units, like uh, 6 may be the length and 1 may be the width. Find its circularity. You have a rectangle particle with the 6 times of 1 units, like instead of giving meter, centimeter, we are giving units. Find its circularity. What is the definition for circularity? If you know that, then this problem is much easier. This is a much simpler one compared to the sphericity. So
Yes, I am doing it. Online.
okay. Take your time.
Sir, seventh one answer is B, sir.
B, point
0.620.
six two zero. Okay.
Yes, sir. Yes, sir.
Anyone else with any other answer? Anyone? So option B is correct. So can you define circularity? Circularity is definition. So perimeter of the sphere having same surface area of that of the sphere divided by perimeter of the particle, right? So
Yes, sir.
that's so just take the surface area. So rectangle has surface area of 6 because 6 into 1 units. This is equal to pi r
6, sir.
square, 3.14 r square. Just a second. And then from here you calculate the value of r value. Once you know the r value, you know the what do you say, r value, obtain the r value. Once you know the r value, you know the perimeter of a sphere, that is 2 pi r, right?
Yes, sir.
2 times 3.14 times r divided by rectangle, that is nothing but, I mean, this is elementary
6.
math, so 2 times L times B. So you can add, and then if you find out, the answer should be 0.620. Anyone with any other answers? Or any doubts with calculating the circularity?
No, sir.
Okay, so let's move to question 8. Which among us the following is used to define the particle shape?
Elongation, sir.
Okay. Anyone? I mean, any other answers? What about all of these?
Yeah, sir. Actually, you already said some three sets of shapes, man. That's why I chose this, sir.
So it is everything: sphericity, elongation, specific surface area, specific surface ratio. All of them are used to define the particle shape. So answer is D. All of the above.
Okay, sir.
So shall we move to question 9?
Yes, sir.
Yes, sir.
Okay, so for measurement of the particle size in the range of 5 to 100 nanometer, which of the following techniques are used? As I said, for handling of the particles, you need to separate them, and depending upon the size of the particles, the separation techniques will be different. So now the size range is 5 to 100 nanometers. What will be the technique? Is it gravity sedimentation, sieve analysis, light scattering, or elutration?
Illustration, sir.
Elutration. So this you can see from that table itself.
Yes, sir.
So let me show. So elutration under gravity is, oh sorry, there is a mistake. It's a micrometers.
Okay.
Hmm. Ah. So this is elutration. So please have a look at this table and try to remember some of these values, because you never know. There may be a fill up or a match the following within this. I mean, I'm not sure, but again, it is my thinking that this may be a place where they can ask questions, or you should know actually this one, so that you will be able to say that once you know the particle size, you will be able to say that this technique will work or this technique will not work. So this is quite important table.
Okay, sir.
So shall we move to the next one?
So the illustration is correct, sir.
Yeah, illustration is the correct one.
Okay, sir.
So question number 10. We will stop with question number 12 for today, because we have, it's already 7. We are supposed to finish at 7, but since we started late, we will extend for another 5 minutes or so. In American standard screens, as mesh number increases, aperture size, how does it affect the aperture size? Aperture size increases, aperture size decreases, does not affect the aperture size. Aperture size increases up to a certain number and then decreases.
Sir, aperture size decreases, sir.
Decreases. As I said, in American standard screens, the mesh number is defined as the is defined as the number of mesh openings per,
Per
or number of
level,
aperture per linear length. So if you are going to have more number of aperture, that means that each size of it is going to be small. So as mesh number increases, aperture size decreases. I hope there's no doubts in that.
yeah, sir. There is no doubt.
Okay. So shall we move towards the next question then?
Yes, sir.
Yes, sir.
Aperture size of an Indian standard screen is defined as I said, if you remember, in case of Indian standards, the definition is different. In case of the American standards, the definition is going to be different.
Sir, option A.
Option A, nearest decamicron of a mesh number. Next question. What is the limitation of screen analysis? When they say screen, it's a synonym for sieve. So both are same only. Screen analysis, sieve analysis. So what is the limitation?
So the particle size below 40, sir.
So you need to have a particle size above 40 micrometers to do the screen analysis. If you have a particle size below 40 micrometers, then sieve analysis will not work out. So that is the option. That is the reason the sieve analysis or the screen analysis is the most primitive techniques that for doing the particle size distribution, particle size analysis. If you have particles which are going to be in more finer categories, or when I say finer in terms of the size, then you need to go for other kind of, what do you say, then you need to actually go for other techniques like alliteration, gravity sedimentation, centrifugal field, ultramicroscopy, light scattering, X-ray scattering, electron microscopy. So I can see with this table itself, we approximately had 2 questions. So you can see it is important one.
Okay.
So I have one question. So this you can take it like a kind of a, what do you say? You can do it in your free time and then come up with the answer in the next session. So particle size distribution of material A is given. That is, within this particular size ranges, what is their particular mass fraction is given. You are supposed to calculate the arithmetic mean diameter of the sample. And then the values are given. So we will not solve this question today, and this question will be posted to you, but solution will not be provided. So we will take up with the problem next week. But before that, I request everyone to look at this question and try solving it, or try to give it a chance to solve. So let's see what the answer is and whether you are able to solve. In case if it is not possible, then we will solve. In case if you find difficult, then we will solve that in the next session. So any doubts for today's live interaction session? I think
Sir, are we have to prove the answer with the theoretic sum
yes.
also? Are we have to prove the sum? Or we just have to say the option?
No, you don't need to like send me. You just keep the answer with you. Next session when we join, if you have solved and if you have got an answer, you let me know. We will solve it in the live interaction session itself. It's just that I want you to, during the week time, you just take this problem and then have a, what do you say, try to solve it. Let's see what, let's see if you find it difficult, then we will solve in the next live interaction.
Okay, sir. Thank you.
Okay. So any questions or anything that you would like to share or regarding how we did this course, any doubts, any feedback on the live interaction session, you are welcome to let me know.
So it's really
Because,
good to know new things about like this, sir.
okay. No, because the
Uh,
problem is we have only 4 weeks. It's a very short course.
yeah.
So, I mean, today already first week is completed. So, that is the reason I'm usually asking for a feedback now. Because if it's a 8 week or a 12-week course, I usually ask it after 2 or 3 weeks. But since it's only for 4 weeks, by the time we start, the course will actually get over. That is the, I mean, that's how the course is designed. So, if you have any feedback, then please let me know. And if you have any doubts also, then please let me know before we conclude our session for today.
Okay, so the class is going to conduct on only Saturday, right, sir?
Yeah. Saturday from 5 p.m. to 7 p.m. So our next live interaction session will be on 1st of August, from 1st of
5
August
to
at the
7.
same time, 5 p.m. to 7 p.m.
Okay, sir. Okay, sir. Because I
Okay,
didn't
sir.
know this timings that my friend suddenly tell me. That's why I didn't join.
Oh, okay, okay. Haven't you received the email?
Yeah, yes, sir. I received a mail, but I didn't check about this.
Oh, okay, okay.
I thought you guys send me a link in WhatsApp or something.
Oh, no, no, no. You will get it in the email. You just, I mean,
Okay, okay.
every week or day before the class, they will send you a reminder email. So just have a, look at the emails that comes from the NPTEL.
Okay, sir. Okay, sir. Thank you, sir.
Anything else? Anyone?
No, sir.
Yes. Oh, okay. So, in case if no one has any doubts or nothing to discuss, shall we conclude the session for today?
Yes, sir.
Okay. So, thank you all for joining today's live interaction session. I hope you find this live interaction session useful. I also take this as an opportunity to thank Professor Shabina Khanam and the NPTEL team for providing me this opportunity to interact with you all on this Sunday after, Saturday evening from 5 p.m. to 7 p.m. Our next live interaction session will be on 1st of August from 5 p.m. to 7 p.m. Same link. So the recording, so this video is actually getting recorded, so you will get the recording as well as the presentation file in the due course of time. So kindly have a look at it, and in case if you have any doubts, you are welcome to email me. My email ID will also be available in the presentation file. In case if you have any queries, you are welcome to email me, or you can also use the Q&A section of Q&A forum for this particular course. So you can also drop your questions there. I will try to answer to them as soon as possible. You can access this live recording as well as the presentation in the course page on the left hand side at the bottom. You can see problem solving sessions. So if you click on that link, you will be directed to an Excel sheet where you will find both this presentation file as well as the live recording. So it will be uploaded to the YouTube. So yeah, so let us meet next week for the week 2 live interaction session. Till then, go through the course and yeah, have a great weekend ahead. Thank you and bye.
Thank you, sir. Thank you so much
Thank
for
you so
this.
much.
Thank you, sir.
Thank you.